So we've established that things can be positively charged, things can be negatively charged, and when they are near each other, then there's some kind of force that either pushes or pulls towards each other. But that's not enough to know, because how far apart must they be, you know? Like, you don't, when you have, like, if you rub a balloon, oh, that's a horrible balloon. Make a proper balloon. Slightly better balloon. Okay. If you have a balloon and you're wearing gloves, right? You're wearing gloves. We know if you're wearing woolly gloves and you're kind of rubbing it against a balloon, something tends to happen when you then bring that balloon near someone's hair, right? There's an unsuspecting person. As soon as you bring it near this person's hair, the hair will kind of start to go towards the balloon. But if this balloon is far away, it doesn't happen. So it makes sense if you then look at the kind of force, right? There's a force that exists between objects that are charged, because what we did when we rubbed our hand against the balloon is we charged it. So something happened to this balloon that makes it want to either pull or not pull at the hair, but it is affected by how close it is to the hair. So, okay, what we can deduce is there's a force, and it has to do with charge, and it has to do with distance. Okay? So our buddy Coloumb, and I'll bring him up right now. This is our buddy Coloumb. Let me just remove him there. Here he is. We just lock him up here. There we go. He saw this happening. Probably not exactly the balloon scenario, but he saw something happening. And he decided, okay, there is some mathematical relationship. So he's going to go define it. So he says, okay, let's say force, we're going to say, is represented by the letter F. It is equal to something, right? All I know is that when the distance is less, so we have a smaller distance, then this force is bigger. Meaning, obviously, if this is closer and closer to the hair, there's a smaller distance, suddenly this force is bigger. The hairs want to go more and more towards the balloon. If it's far away, you know, it doesn't really. So we've got that. Higher force, less distance. Then he realized, okay, another thing is this force only happened when we first rubbed the balloon with our hand a lot. I mean, sometimes it works if you just bring the balloon close to the person's hair, like a few would go up. But when he rubbed the gloves all over this thing, then suddenly a lot more hair would go up. So this charge and the amount of it has something to do with the force. So the more charge there is, the higher force there is. I'm going to say more charge, like that, right? So this is what he could establish. Now, the only thing he had left to figure out is by how much does the force go up if the distance is less, and by how much does the charge, or how much does the force go up if the charge goes up? So with a bunch of experimentation that luckily we don't have to figure out from the start. I mean, you could derive it for days, but we're rather just going to say the formula. He discovered that the formula that relates all of these together is F equals K times Q1 times Q2 over R squared. The end. No, I'm kidding. We have to say what these things actually mean. So, firstly, it makes sense. F equals something divided by something. Anything in the top, or the numerator, so anything in the top, if this goes up, obviously the force will go up. If you have 2 times 3 equals, let's say, we have the answer equals 2 times 3, okay? This at the moment is 6. If we take anything, divided by 2, okay, 6 divided by 2 is 3. 2 divided by 2 is 6. 6 divided by 2 is 3. 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 6 divid I'm just trying to show you how this goes up. So we have something equals some kind of thing at the top and something at the bottom. Obviously, 2 times 3 is 6. Divided by 2 is 3. What if we replace this 3 with something bigger? 5. Now we have 10 divided by 2 is 5. You can see this goes up. If anything at the top goes up. If it's divided by something bigger and bigger and bigger, like now it's divided by 3, this will be a bit smaller. And now 5, it's a bit smaller and smaller and smaller. So this makes sense how he figured out the formula will have something on the bottom. If he wants this thing to go up when something else goes down, so where distance gets smaller, then force goes up, then that means this other thing has to be at the bottom. If both go up, and they interact in that way, they are related in that way, then they go at the top. I hope that makes sense. Okay, so r squared refers to the distance. So he figured out, okay, in this formula, the amount by which the force goes up is related to 1 over r squared. R is the distance. R is the distance between the charges. So this person's head is charge number 1 and this balloon is charge number 2. Obviously there was actually, let's say charge number 0 actually transferred things there. But I'm just going to talk about what happened after we made this balloon full of charge. Yeah, so this distance, r squared, this would be r. This is getting a bit messy, so I apologize for that. But this would be r. And it would be squared. I think they give you this formula. I'm not sure. But no, they would give you the formula. Okay, so that's what r squared is. R is the distance between charges. Then we have Q1 and Q2. In electrostatics, we like to say charge is Q. I don't know why. We just decided that, hey, we're not using that letter for anything else besides in fluid mechanics, but that's a whole other ball game. But and actually also in heat transfer. But there are other subjects where Q means how fast something is flowing. There are other subjects where Q means how much heat energy travel. It's a whole thing. But don't worry about that. In this subject, we decided that Q means charge. And we measure it in coulombs, but I'll get to that in a moment. This man, he is like, yeah, let me be a measurement. So in this case, Q1 means charge number 1 and Q2 means charge number 2 because we're looking at 2 objects right now. Then we have this last thing called K. That is just a constant. He was like, okay, everything here reacts in the way that we expect it to if force goes up, if Q goes up, and R also... When R goes up, then force, if R goes down, the smaller distance, then force increases. But there's something missing, and he just slapped a nice constant in front of there. And he found that worked to perfectly explain the force. So, in short, Coulomb's force, or Coulomb's law, is just the expression that relates this force that exists between electrostatic charges. Go. Okay, so I paused it because people walked in and tried to look over my shoulder, but now I'm just going to continue. Okay, I am played. So in short, this force that exists between electrostatically charged objects, just meaning that they have some kind of number assigned to them that describes the amount of electrons in them, but you don't really have to go into that much detail. This force that exists between them is equal to some constant that we have called K times Q1, which is the charge on Q1, which we will go into. I'm just going to go over the overview of this formula, times the charge on Q2 over the distance between them squared. That is literally all it is. We will go into what these are. This number, I hope, will be given to you. What are you guys laughing at?
I'm laughing because you sound angry.
Do I sound angry? I'm still recording this.
It's that simple.
What?
You're like, it's that simple.
It's that simple. I've decided it's simple. Okay. I will go into the detail of what these specific parts of the formula are, but I just want to give you where this formula comes from so it makes sense about how it functions. The exact definition that you have to know is literally just this formula put into words. So they look for a very particular definition in exams, especially in grade 12, where you have to study the grade 11 definition as well. But I'm just going to show you that it's literally the exact formula here. So this definition is, or if they ask you, what is Coulomb's law? So Coulomb's law, question mark, is this means the magnitude of the I'm just going to write the rest. Okay, so the first part of the definition is just saying what are we actually talking about. The magnitude being how big, or the number, so not the force, but actually how much of the force, the magnitude of what? The electrostatic force, right? Because we're talking about the electrostatic force exerted by 2 point charges Q1 and Q2. So what can we say about this magnitude? Okay, so how do they relate? What do we have to say about this force? Well, it is directly proportional to the product of the magnitudes of the charges. So this is just big fancy words for this force. It goes up as this goes up. Directly proportional means that as it's proportional. Proportion means if one thing goes up, the other one... Guys, stop laughing at me. This is why... I'm going to pause.
It's proportional.
It's proportional. I slipped over my words, but it goes up if something else goes up. Directly proportional means it is going up as the other one goes up. 2, this value, which is the product, means something times something of how big the charges are. And it is also inversely proportional, meaning something else goes up and this goes down. So it's whatever is beneath the dividing line to the square of the distance between them. The distance between them is that r, and then square is obviously to the power of 2. So just look at this definition for a while and realize that it is literally the formula just put into words. So if you ever forget a definition, just check the formula sheet.